Hello, my good phys heads. So here is that classic bowling ball problem. Got a bowling ball of mass m and a radius r. It's tossed with a horizontal velocity onto a bowling lane and has no spin initially. The bowling lane has a coefficient of kinetic friction, and so there's a kinetic frictional force. And eventually, down the lane, some distance d, after some time t, the bowling ball is rolling without slipping. So rolling without slipping. And we're going to find the time, the distance, the final velocity of the center of mass with respect to the initial velocity of the center of mass. And we're going to do that following a format that's given in this problem, which I stole from Dr. Brown. And we're going to finish by finding the velocity at the center of mass by just using a different technique, which makes it much easier. Here we go. So for part A, we use the suggestion to find the time by starting with Newton's second law for rotation. Torque equals the rotational inertia times the angular acceleration. Take the torques about the center of mass. R cross F is perpendicular, so the sign will be 1, and we just get the radius, which is the distance from the point of contact of the frictional force with the ground up to the center of mass, times mu sub k times mg. That would be the frictional force, and you can verify that by going through sum of forces in y and all that if you want. But the normal force would be equal to mg, so the frictional force is the coefficient of kinetic friction times mg. Whoa, hey there. Cutting in on myself to say I should have mentioned that you need to recognize that the only force exerting a torque about the center of mass is that frictional force. So what I wrote down was the net torque about the center of mass, considering all the forces acting. All but the frictional force have a line of action through the center of mass, so no moment arm, sum to 0. Signing off. Moment of inertia for a sphere is 2/5 mr squared. And then I wrote the angular acceleration as the time derivative of the angular velocity, minus the vectors, so we're working in sort of one dimension now that we've taken the cross product. Separate variables, integrate, and you get the angular speed as a function of time. From that equation, and recognizing that the initial angular speed was 0, that was the constant of integration, we can solve for the time. And so the time between the bowling ball striking the lane and rolling without slipping, which is at some final angular speed, is twice the radius of the sphere times that final angular speed over 5 coefficient of kinetic friction times gravitational constant. It's not really what I mean. It's gravitational acceleration, but in this context, I really like gravitational field strength, that familiar 9.8 newtons per kilogram. In those units, I think gravitational field strength. To find the distance traveled before this bowling ball starts rolling without slipping, just start with the kinematics equation. There's a constant acceleration of the center of mass, so the position of the center of mass as a function of time is given by 1/2 acceleration times time squared, plus the initial velocity times the time, plus the initial position, which we're going to set equal to 0. To figure out what the acceleration is, you can use Newton's second law for translational motion, and we've got that the acceleration is negative the coefficient of kinetic friction times that gravitational field strength. So doing a little bit of algebra after plugging into that kinematics equation and writing x sub t as d, this moment in time when the bowling ball just starts to roll without slipping. So we substitute all that stuff in there, and we get that the distance the bowling ball travels down the lane before it's rolling without slipping is 2/5 the final velocity of the center mass over u sub k g times the quantity, which is the initial velocity, minus 1/5 the final velocity. Notice that at that moment in time, when the bowling ball is rolling without slipping, the rolling condition is satisfied, and so I had substituted in there the final velocity of the center mass is the final angular velocity times the radius of that sphere. Next. All right, so for part C, to find the final velocity in terms of the initial velocity, we can start with another kinematics equation, plug in that moment in time, the acceleration that we knew, and a little bit of algebra. Very quickly, we're at the final speed of the center of mass is 5/7 the initial speed. All right, now for part D. All right, so for part D, the suggestion is to take torques about the point of contact of the bowling ball with the lane. We'll call that point P. Notice that now the torques about that point are zero. The frictional force, the normal force, the gravitational force, they all go through point P, point of contact with the ground. So that means that the torque as the time derivative of the angular momentum would be 0. Therefore, angular momentum is conserved. All right, so right when the bowling ball begins its traversal down the bowling ball lane, it has no spin about the center of mass. And we would just have the angular momentum is r cross the linear momentum. So RMV, those are right angles, so sine of the angle is 1. And we've got if we define clockwise rotation sort of as the positive direction, then we've got a positive RMV sub naught, which is the initial velocity. Now, when this finally gets to that point, when the bowling ball is rolling without slipping, and we're at that final velocity of the center mass, which is equivalent to the final angular velocity times the radius, because we have that rolling condition, then the final angular momentum will have those two parts that spin about the center mass and the angular momentum due to translation that we had discussed in class. So if you do the algebra, plug in our value for the rotational inertia of a sphere, and simplify, you get the same result we got for part C. But wasn't this easy? Fun.